Testing. Okay. You'll just take. Having issues with the slides. Yeah. So right now they'll just be the same. That one's muted. That's fine. The two lenses, so it kind of acts like eyes.
so it can tell how far away things are. So it would know like this is maybe 1 meter away and it's at negative 60 degrees from forward. So then we know where the camera is. Based on that information, we can plot the point for where this tag will be, or whatever it is, an obstacle. So, and then we just have a big list of GPS coordinates and obstacles. It's just basically at the very front. It's like where the arm goes in the science system, they all swap out. So we just have this on for the autonomy task. If you look at the old Rover, like you'll see 2 bars sticking out the front, and the older one, yeah, it basically just goes on the very front. Like it's the head of the Rover. What do you mean exactly? Like, oh, play with it? It's actually a pretty fast Rover this year. We were drifting it in the golf course last week, and so Rover's about 3 times faster this year than it was last year. Can you tell what? Where this year we took a detection approach where basically can look at a 2D image and find the object based on what we trained it on. So this is it's a fast way to do it. Last year we had an approach where it basically plot everything it sees as a 3D image, and then so in that case it would plot like the hills, and then it would basically take out the ground and anything left was an obstacle. So this is effective if you don't know what you're going to be running into. But the problem with this is it's very computationally heavy. So it takes a lot of time to run it. It's usually really slow. And so for us, it was just too slow. So we switched to this approach because we really know, in most cases, we know what we should be encountering in Utah. It's not like there's a bunch of random obstacles. So we basically we get a bunch of pictures of it. And like Clayton was saying, you just draw a box. You say like, you take the picture and you say what's in the image. You manually label it and tell it what it is. And then it runs it through a program, and then it spots the patterns between each instance of that object. And then it can build up an algorithm basically saying these pixels look like this object or not. So basically you just have to add, thousands of instances of that object so it can tell. Like, how many instances do we have of an object usually?
1,000 images. I think we've got about 1,200 people combined. Another 1,000 trees, and like 800 rocks, our tags, and 600.
It's pretty bad. Once you hit 1,000, it's decent.
Yes, I can. Am I talking to the microphone? All right. So, this is the station for our custom-built fluorescent spectrometer. We have right here a sample of an amino acid called quinine. And when exposed to a black light or UV light, it fluoresces or glows. And that's exactly what we're measuring. We have the LEDs. We have the LED boards right here that focuses to the sample. And then it goes through here to the diffraction grating where it's spread across a sensor in a spectrum like this. And after that, we can read whether or not there's life in a sample.
Can you talk about your system?
Is it working? Okay. All right, so this is the sound analysis part of the Mars rover design team. Basically, our goal is to see if there is life in whatever we're looking at. So our competition will give us soil just like this, and we will have to use various methods to see if there's any life in there. One of our methods is actually using a microscope, and we can see these rocks and particles in here. We can kind of see, is this the right stuff that could have life in it? Another thing we have is chemicals. What's happening? Damn. Rest in peace. Do I start from the beginning? Okay. So another thing we have to detect life is chemicals. So right here we have an example of fluorescence. When you shine a light, light's not even there. Hold on. All right. When you shine a fluorescent light on this chemical, it will actually shine a different color. So that's one of the things we are using to detect life, because all molecules will fluoresce at a certain color. They kind of shake a little bit, and then that bounces a different color, and we can see that and see that there's something in there. We also have different kind of chemicals that will change a color when something is present. So right now our chemicals are looking for proteins and also sugars, both things that life needs to, keep going. And lastly, one of the newest things, the addition to the Mars rover design team science analysis, is our fluorometer. So, okay. Yeah, we are super excited to use all of our technology in this year's competition and see what we can find. Yep.
Jacob, can you tell us about the autonomy?
So in the autonomy task, our goal, here's an example goals, we'll be looking for a tag like this, and they'll give us a GPS coordinate within 60 feet of that tag. And then from there, we need to drive within just 6 feet of the tag and then flash our lights to show the judges that close enough and we finished. So here's some example technology of what we use. This is the autonomy head, so it has a topic camera and then 2 more cameras on the side. From here, this is one input we're getting. This shows what objects we might be running into. So in this case, it's picking up people. And then if we find this, we can see how far away they are, what angle they are from us, and then we can avoid them. This one finds our AR tags, so you can see right here it's outlined. And then can you move that around? Can you just pick it up? And then it follows the tag. So that way we know where our goal is and we can drive up to it. This camera at the top, it has 2 lenses, so it kind of works like your eyes. So you have 2 different images, and based on the difference in the images, you can tell how far away something is. So with this camera, we can say this image is maybe 2 meters away and 30 degrees to our left, and then we can plot that point so we know where it is relative to us. That way we can tell if we're close enough or if we're far enough from obstacles and stuff. Can you change to the sim, Clayton? All right. So he's showing the how we train the detection model, which is basically we get a large set of pictures, and each picture we outline an object and we label it, and then the program will find the patterns between each of these pictures to let us know if that is that object or not. So each like we've trained the object going to be like 2,000 different people, and it can spot the commonalities between those. So now we have the sim open over here. This allows us to test. So setting up the rover and testing can sometimes take a few hours just for prep time. So this lets us test efficiently whenever we have new code and we just want to see if those small changes work. It also, everything in there is absolute. So the GPS is perfect. There's no like outside factors that could affect it poorly. So we know if the code is behaving improperly, that it's a fault of our logic and not something like the electronics GPS. So this is good for just knowing that the code itself is good, so that when we go outside and test it, any other problems may be an outside source like GPS. So that way we know how to account for things and fix it. Anything to add, Clayton? Yeah, that's autonomy.
What am I doing? Is this an interview?
Explaining what's going on.
Explain what's going.
The lights.
Explain to the boards. Okay. Well, this is the electrical. This is the electrical table. Here we have all of our PCBs we make every year. We start from scratch. We design all of them from scratch. Get them. Separate company actually manufactures them. But once we get the blank boards like this, we assemble them all until we get a finished board like this. Have a bunch of different boards. So we have power board, for example. This takes power from our battery, distributes it to all the other boards on the rover. Got BMS. This plugs in directly to the battery, monitors the battery voltage, battery current, make sure the battery's safe to operate. We don't want the battery to be unsafe. We have drive board. Drive board controls all the motors that on the rover, so we send it a drive command, go forward, go back. It translates that all to commands to each individual motor to make the rover go. Also got gimbal board. All of our cameras are on little servo motors, so what happens is we want to actually be able to move the cameras to see, so we have a rotate and we have a pan as well, so that way we can see in any direction we want with our cameras. Also have nav board, tells us where we are, has GPS on it. We use it for our location whenever we're doing autonomy. Yep. Okay.
This is a live.
Oh, hello. I mean, sure, I can talk about anything. So this right here is one of our custom-made carbon fiber wheels. It's not fully finished yet. The finished ones are on the rover at the moment. But what we do is we take this mold and we layer it with carbon fiber. You can see that sometimes we use Kevlar just to get different levels of strength and such, resistances, so on and so forth. And what we do is we layer it with a lot of different epoxies and go layer by layer to integrate all of that, put it in an oven, and it comes out like this. Now this is only one of the stages, obviously. This whole table is a lot of the, we got some carbon fiber stuff, that's more stuff on the wheels, so on and so forth. But the whole thing that we're trying to do this year is, first of all, replace some of the components with carbon fiber. You can see that with the diff bar and the experimental diff bar here, because carbon fiber, when engineered correctly, we take no strength loss, sometimes even gain strength, And additionally, you're going to see it'll hold up really well and be a lot lighter. That's what we're going for. We want to save as much weight on the rover as possible so we can put it towards other new systems. If you've seen science yet, we're trying to put a fluorometer on there this year. So we got to get that weight somewhere. So we're cutting things where we can. We're engineering new solutions to continue to be here today, tomorrow, forever.
I don't know that we have much. Hi. How are you guys? You in the front?
So, PlayStation, it's the computer that we use to interface with the rover remotely. Every tool that we need to interact with or control the rover, it's done here. So over here on the leftmost screen, that's the Rover Overview of Network, or RON for short. This is all the tools that we need to monitor our connection and monitor the data or packets that are being sent in between the rover. This is Rover Engagement Display, or RED. This is sort of our master interface. This gives us sort of a broad, the most important controls that we need to interact with the rover. We have like the map and GPS controls, and then battery monitor and speed limit control scheme. Over here we have the Rover Imagery Display, or RID for short. This is just the big camera screen so that we can see what's going on. Over here are our subsystem controls. This is everything that you need to control the arm. This is everything that you need to control the science system. And then this is everything that you need to run autonomy.
Hi, Grandpa.
Great. Can you tell us about signal stack?
Sure. Alright, so this signal stack has two different frequencies that we allow it to use, 900 megahertz and 5.8 gigahertz. And essentially what we can do is we can rotate it to whatever angle we want. So we have a stepper motor on the signal stack here. We can send either just step commands, and we're working on sending position commands as well, so we can have it point towards the rover and get better signal connection.
Hi, Mom. Also, Today, Tomorrow, Forever has changed its meaning for me, like, every step of the way that I've been on this team. It definitely started when I was just a member as something I just wanted to expand my knowledge on. I didn't really know anyone, and I just knew that I needed to learn more. But now I would say that I'm here because I like the people that I'm here with, and they feel like my family at this point. So, you know, you want to spend time with your family and do things with them, and they definitely push me to be better. So I'd say that today I'm here because I feel like I'm learning and growing and like learning and growing with other people. Tomorrow, I'm learning so much and I want to help others learn as well. So I like teaching people and paying that knowledge forward so that forever we can, and people after me, go out into industry and be productive and helpful engineers and try to leave our mark and make an impact and help things. So, yes. Thank you, Abby.
So the actual arm is back being put on the rover by now. Once the rover rolls out, you'll be able to see that. Here we have some different R&D stuff we've been working on. So we have some different R&D stuff for ARM we've been working on here. These are a pair of carbon fiber plates we're going to use to replace a aluminum part on the bicep. So currently, they're a little bit floppy. That's because they're not spaced apart any. So what we're going to do is take these, add some aluminum inserts for where it attaches so we don't have bolts going through carbon fiber. And then stack it up with a piece of core material here in the middle. This Nomex stuff, but you can feel it. It's very light. It just exists to take space, so you can space your components apart, increase the moment of inertia of the part, and make it a lot stiffer. So this will save some weight over the aluminum equivalent, and it should also be significantly stiffer. Because carbon fiber is like a fabric. If you've ever had like a thread you're pulling on or a rug or something, in tension, it takes a ton of load. So when the arm's being bent, when it's put under tension, the part won't deform much, which will lead to more accuracy for the arm overall. There's also a mechanism here, a R&D wrist. So this would go at the end of the arm. We'd put the gripper on the front here through these little threads. And then this gives us our 2 degrees of freedom. Notably, our current wrist is a set of diff gears, which requires a very large, very wide forearm. We'd be able to replace that with essentially half the amount of metal. And there's less backlash in this than our 3D printed gears. Another prototype joint that when the arm looks out, this looks cooler because it's about a third the size of the corresponding joint on the arm. We eliminated the requirement for a slip ring, so it can get a lot smaller. And then also have a prototype cyclodal gearbox here. Can you hold the microphone for a bit? So this guy, if I go ahead and spin it, you can see how much slower the output is going compared to the drill. This is about a 15:1 gearbox, and it's a very nice form factor for robotics because these guys tend to be very compact, very flat, and they can get very high gear reductions.
Oh, do I have to?
Yeah. Sound check. Testing, testing, test 1, 2. Testing, testing, test 1, 2. Testing, testing, test 1, 2. Test, test, test. Test.
We turned on the gain on that?
Testing.
Or I could just not use the microphone.
Okay. Then we can just put this level down, and I'll just talk really loud at the mic away. Yeah. Testing, test, 1, 2. Cool. That can be a game time decision. Yep, sounds good. Excuse me, everybody, excuse me. Okay, squeeze through here, folks. Pardon me, pardon me. Microphone troubles. Yeah. Hello, everybody! How's everyone doing? All right, guys, I'll have to bear with me for a minute. We're having a couple of audio issues, so we're not going to have a microphone for you guys, so I'm just going to talk really loud. The people on our live stream hopefully are getting some level of decent audio with this microphone. But thank you all for coming to the 2023 Rover reveal for the Mars Rover design team at Missouri S&T. For those who don't know, my name is Max Ryan. I'm the current Chief Executive Officer of the Mars Rover design team, and I'm here to talk to you guys about just some really impressive people that we have on our team today. You know, the fact that we are a design team that builds a rover, the fact that we are a design team at Missouri S&T, the fact that, you know, we even put such a big emphasis on the manufacturing part of our systems and our rover, that doesn't define who the team is, in my opinion. What defines who our team is are the people that make it up, the people that are putting in late nights, the people that pour in their heart, soul, and passion, the blood, sweat, and tears that everyone feels when they're on this team, the sense of pride and passion, not only in the work that they can take ownership of, but the work that your friends are taking ownership of, but the work that your family is taking ownership of. And the fact that we have such an incredible group of people here today, in not only the team members, but all of you being able to gather with us, is just something I'm really, really proud and fortunate of, to be able to have all of you here today. We've put in a lot of work over the past, couple of months. You guys are going to be able to hear a little bit later about some of the technical advancements that we made from Keaton, our CTO. We're going to play our system acceptance review video, which is a part of a video and essay package that we actually have to make to get into competition. You know, people often think of design teams as engineering teams alone, when that could not be farther from the truth. As you will often find in industry and many walks of life, communication and being able to relate to people on a personal and human level is what defines us and how we're able to communicate and connect with each other. In order to get into our competition, we can have the most perfectly engineered rover. We can have something that will never break, something that is indestructible, something that is going to win just point blank. But if we can't communicate about what we do on Rover, if we can't communicate how we do things and why we do things and what drives us to do these things, it doesn't matter. In order to get into competition, we have to write a technical paper and produce a video so that we can actually be allowed to go on site to compete. And the fact that we are not only able to engineer an incredible rover, an incredible device, the fact that we're able to do all of that together while holding events like this, while being involved on campus, while our team is, among the highest of S&T population in terms of grades and GPA, the fact that we can do all of that and we are still competitive year in and year out is just simply incredible. We're going into our second decade as a design team. This is our 11th year. We celebrated our 10th anniversary last year. And the fact that, the work we're doing today can last for that long. The fact that the work that each and every member of the Mars Rover design team is doing right now has the potential to last that long and have that much of an impact, not just on the team and the university, but on the students themselves, is unheard of, in my opinion. We're not able to do that just by ourselves. We have an incredible support group that I feel I have to thank. They are the people that help us do what we do. I can't thank them enough. Thank you to Mo Dagani and the University of Missouri System for challenging us in ways that you don't see in the classroom, for challenging us in ways that you're facing these challenges, these bumps, these adversities every single day, because that is what you'll see in industry. Thank you to the Design Center for giving us such an amazing facility in order to do everything that we do, for us to manufacture, for us to give students the ability to not just design, but design with the intent to manufacture, design with the intent to go out and do something in the world. Thank you for that opportunity. Thank you for every single person on the team. As CEO, my job is honestly pretty great because I get to lead an incredible group of people doing all sorts of incredible things from all walks of life, from all disciplines, from all technical backgrounds, all different skill levels, everybody. It is just an incredible team to be a part of, an incredible team to lead. I've found my friends and my family on this team, and I am excited and just cannot wait for the competition season ahead, because I have complete faith that we will be able to crush the entire competition. For those who don't know, I just said this is our 11th year as a design team. Our first year as a team, we took 10th in the world. It's pretty impressive until you realize there are only 10 teams competing. But the year after that, so many teams applied that the organization putting on URC, the University Rover Challenge, the Mars Society, actually had to put a limit on how many people they could put on site. That limit is currently 36 teams. 36 teams from around the world are only allowed to the Mars Desert Research Station every single year to compete in this international competition. And the fact that we are consistently among those 36, not 36 or 35, the fact for the past decade, we have been top 5 in the world ever since. 3rd last year, 1st in 2017. The fact that we are going to do this again this year, that kind of legacy just doesn't happen. That legacy needs determination. That legacy needs drive. That legacy needs passion. That is something that we're going to do. That is something that I have faith in every single one of our members to be able to do. To talk a little bit about the history of the team, I want to invite Dr. Melanie Mormile, our primary advisor, up to the stage so that she can kind of say a few words about where we stand in history.
Wow, thanks, Max. Thank you all for being really supporting this. Saying, somebody asked me how long I've been with this team for a while, but I've been with the team ever since it's launched. And in fact, it started, I would have, thought to be this crazy professor teaching this microbiology. But these 2 young men, Michael Bouchard and Ian Lee, came into my office and they were like, we have this idea. We'll being the advisor for a team that is going to build rovers that can help astronauts on Mars. And I was like, yes, that sounds phenomenal. And I'll tell you, I really had no idea what I was getting into. And in fact, a couple of years ago, I made a point of telling Michael, thank you for asking me to be that initial leader of this team, because it has just been so incredibly rewarding. So, and frankly, it's not me. It's working now? Oh, okay, thank you. That's why I'm like shouting. So it's just been incredible. And I don't necessarily really want to go into the blow-by-blow history of this team. You can go to the website and see that. But one of the things I really want to emphasize to you is the whole concept of the today, tomorrow, forever theme that runs through the particular team. So today, you are witnessing what the team, this current team, is accomplishing. And typically I try and damper, the team a little bit. That you might have to expect or to accept something besides number one. But this year we're going to take number one in the world. Okay, this is the year. This will be the second year we're number one in the world. But so that is today. Okay, tomorrow is the development of the scientists. I'm a scientist, not an engineer, but the scientists, the engineers, and actually the people that we need to support our scientists and engineers, those technical writers and all. And so things that, or what I want to sort of really bring to your attention is our wonderful alumni base. So people from our team have graduated and gone on to phenomenal careers. So actually Michael Bouchard is living his dream. He is a scientist at the Jet Propulsion Lab, so which is just mind-blowing. A number of our students have gone on to NASA. Currently, actually, as Sean was telling me earlier, with Relativity. If you haven't heard of Relativity, check it out. It is a company that is 3D printing rockets. So have they launched yet? Oh, darn. Okay, but they'll make it. If it's not today, they will make it. But our alums are doing things like that, going into cutting-edge businesses and companies. Others, they're going into their family businesses. They're earning PhDs. I cannot be prouder of these people. And frankly, yes, I'm looking forward to our competition this year, but I'll tell you, what I'm even looking more to is seeing what this particular group of students are going to accomplish after they graduate from Missouri S&T. So I'm seeing the bigger and better doing. And then the future is actually doing that outreach, interacting with kids and getting them all excited about science, engineering, and space and everything. And our team does an excellent job with that. And so, again, thank you all. It's great seeing everybody. And then, Max, am I supposed to turn this?
Dr. Mormile, everyone. Alrighty, so without further ado, if we could please make a hole around the garage door in the wall as we unveil the red carpet for Helios, our 2023 rover, the 11th rover in the history of the Mars rover design team. Helios! I got chills, everyone. All right, so Helios is going to be available at the end of the event for people to take pictures with. I know some of you might have to leave. We're going to be here for a while, but while we're here, Keaton, are you back there? Yeah. While we're here, Keaton is going to give us a little bit of an overview of some of the notable technical details of the rover. After that, we have a TV in that corner of the room that we are going to watch our system acceptance review on. And then after that, we're going to have a panel of some of our team leads to be able to answer some specific questions about why we did certain things with the rover, why we made certain decisions, and all sorts of things. We would really appreciate it if you can stick around. I know not everyone can, but I'd like to thank you all for coming to our event. I'm really proud of not just the rover, but this team as well. Thank you.
All right. So, like Max said, I am. This is the door. Good. So, I'm Keaton Rofer, I'm the CTO. I'm just going to go over a little bit of the technical side of Helios. Before before I do that, I just want to thank you guys so much for coming. That we could not do this without our members. We could not do this without the support of their family, our amazing alumni. And, you know, when we look at this rover, we're going to talk a lot about the new things that are going on. But I think that causes us to forget about the amazing things that we kind of take for granted, that we just do every single year is just normal to us. We do these things every single year and we don't even think about it, because to us, that's just the way it is. And that really is due to the support of our amazing alumni to give us, you know, that platform. Some really impressive, amazing things just seem normal, just seem every single day. Like Max said, you know, we've competed in the Mars Rover Design Team, or the University Rover Challenge, for 11 years. We design and build a new rover from the ground up every single one of those years, including in 2020 during COVID. Every single year we redesign, rebuild a rover, and we take a new rover out to Hanksville, Utah every single year. Okay. Every year, our team is driven by the freshmen. It's not driven by the leads. Leads are there to teach people, but it's the freshmen who come on, they design everything, they build everything, and we have to go through and take a member who knows absolutely nothing about engineering, potentially, and in 2 months, give them all the skills that they need to build a world-class Mars rover, to build a Mars rover that is capable of being top 5 in the world every single year. Like I said, we manufacture all of our parts. All those composites on the rover, they're done in-house. All the aluminum machined in-house. All the PCBs designed by us, assembled in-house. From a high level, we write all of our own software. Again, every single year, we do it all entirely custom. That includes writing a custom GUI system, so a graphic user interface, so we control the rover, so we can interact with the rover, and even a custom network protocol so we can communicate with the rover. Again, entirely custom, stuff that we take for granted because that's just every day for us. We design and assemble all of our own PCBs. We even make our own custom lithium-ion battery pack. We need one, we don't buy it, we make it. Again, every single year. We develop innovative approaches to test for life in geologies and the environments that are closest and most analogous to Mars. We go out to Hanksville, Utah, we're looking for life, we're trying to answer the question, is there life? And again, we're coming up with innovative approaches to that every single year. This team does that. This team comes together to do that every single year. As far as this year, I'll start with the core systems. Some really impressive things have happened. First of all, it's the 6th iteration of our Mantis suspension. Max talked about legacy. I came to Missouri S&T because I watched a video on YouTube about the Mars Rover Design Team making their own custom suspension, unlike anyone else in the world. To me, that was a legacy of this team, and it's something that I'm proud to say that we maintained and upkept because it is the best in the world. We're going to upkeep it and use it because it's the best in the world. We will change it though. We will innovate on it. So we've done some innovation this year. We've made manufacturing lighter, or made manufacturing easier, made the rover lighter, and it performs just the same. We're continuing to use a 6-axis articulated robotic arm. Again, all of this every single year to build a 6-axis robotic arm that can do everything a human can do, just maybe a little bit harder, maybe takes a little bit longer. Well, if a human can do it, our robotic arm can do it. And the thing is, with that, you need to control it. We have something called brushed motors. There's a way that you control them. You can buy them. Unfortunately, due to the chip shortage, we weren't able to do that. We weren't able to buy the motor controllers. However, if you saw the demos earlier, you'll saw the arm still move. That's because our electricals took it upon themselves, said, if we can't find it, if we can't buy it, we'll make our own. So they developed their own custom H-bridge circuit so they can control brush motors. And then we led to a signals overhaul this year that, I would love to go into great detail and explain. Unfortunately, I'm not smart enough to do so. My friend Brady Tapple is, and he's gonna hate me for calling him out. But you should go talk to him and let him explain just the amazing signals overhaul that we're doing to, go out and do better at competition. Last year at competition, we got 3rd in the world. There were 2 major tasks that, if they'd gone slightly differently, we would have won 1st in the world. Both of those were caused by signals errors. This team got in the trucks, they got in the vans, they said, they looked at each other, we all looked at each other, and we said, we're doing a signals overhaul. That's never going to happen again. And we've done it. And it is some impressive stuff that you should ask the people working on it. They're doing amazing things. The science system, we have a science system with different chemicals that look for signs of life like proteins, amino acids, and sugars. We developed a water multiplexing system to extract potential biomaterials from the soil, and then custom heaters to accelerate the chemical reactions that happen in those soil samples. A soil cache system so we can collect soil and deliver it to the judges. An updated instrument array with custom UV fluorescence spectrometer. That is just an amazing thing to see. These are instruments that NASA is going to use, and for our members to go and develop versions of that here in-house, entirely custom, where else do you get that experience in the world? There's nowhere. Our autonomy system, we have stereo cameras stitched together with wide-angle cameras, create a large field of view system. Have you guys seen little robots driving around Raleigh, the little Starship bots, the food bots? That's how they work. They use multiple cameras, take multiple images, they stitch that together, and they run algorithms on that. That's what we're doing here. They develop A-star pathfinding algorithms and optical positioning tracking systems to know where we're at and navigate the terrain. And then, whenever they are navigating the terrain and they run into obstacles, it's okay. It doesn't matter. Because we have neural networks developed for obstacle detection. We can find obstacles, see them, and then avoid them. Again, this is industry level stuff. This is cutting edge industry level stuff. And we do it right here as freshmen every single year. And then beyond that, we've just developed an R&D division this year to make huge advancements in composites, to develop, and aid our, comp size and developing, the signals overhaul and developing a rotating signal stack, looking into advanced processes like electroplating or powder coating our materials. It truly is an impressive rover. And again, if you look at this rover, very impressive. I encourage you to take pictures. But know that we develop a rover like this in-house, custom, 100% every single year. Where else do you think you can find that in the world? Where else do you think you can find that at college? You're doing that as freshmen, no requirements whatsoever, and we're one of the best in the world. I'd be happy to talk more about the rover, but truly, I do think you should ask the members here and the team leads here. Something that is so special about this team is that the team leads, we're just here to guide people and train people. It's the freshmen, the members, who are doing all of the work. So if any of that sound impressive to you, find a member and ask them about it, because they're the experts, they're the ones that did it. Thank you, guys.
Now we'd like to share our system acceptance review video with you all. Those things, talk about all those innovations that we made. We like to think we captured them very well in our system acceptance review. So if you all could turn your attention to the TV over there, that's where we are going to play for you. If for whatever reason you cannot see or would like to watch it later, it is live on our YouTube channel right now. If you search Mars Rover Design Team, it'll take you to our YouTube channel. And then after that, we're going to hold a Q&A panel with some of our team leads. Since the end of URC 2022, the Mars Rover Design Team at Missouri S&T has been hard at work researching and refining both our novel and legacy systems, so that through a combination of computer-aided design, finite element analysis, bench tests, and task simulations, we will be able to meet all competition requirements. The Mars Rover Design Team is proud to present our 11th rover, Helios.
Helios features a signals overhaul this year. A managed network switch runs 900 MHz, 2.4 and 5.8 GHz bands simultaneously. A Jetson Xavier streams up to 8 parallel camera feeds over UDP, while GPS is improved through a differential positioning system. A custom 8S8P lithium-ion battery with current sensing and active filtering capabilities powers a 14 PCB distributed architecture. To interact with the rover, MRDT has written a custom GUI application in which operators are able to see and easily switch between camera views, monitor the rover's location on a map, position the rotating signal stack, and view diagnostic data sent from the rover. These systems provide operators with an insight into the rover's state, while an attachments manager displays results from the science hardware and allows precise control of the arm.
Helios features key modifications to our legacy Manta suspension, greatly reducing weight, design, and manufacturing complexity while maintaining similar performance. Featuring a structural composite frame, carbon Kevlar wheels, and a modular auxiliary mounting system, our rover is capable of withstanding a 1-meter vertical drop and full-speed collision. Helios can reliably produce a max torque of 13.2 Newton meters, a max speed of 6 meters per second, and traverse a max incline of 45 degrees. Paired with a 6-axis robotic arm, our rover has the ability to locate, pull, lift, and carry a large range of tools and objects while traversing sandy, rocky, and uneven terrain. Our camera and gimbal system allows base station to view the state of all systems during the missions while providing greater viewing angles during operation.
Helios' new 6-axis robotic arm gives it the fine control, strength, and range of motion required to successfully complete the equipment servicing task. An inverse kinematic PID control scheme actuating through custom H-bridge motor controllers and brushed DC motors enables fine control of each joint. A new combined end effector design is both simpler and lighter, while maintaining the ability to lift a 5 kilogram weight, open drawers and cabinets, tighten a hex bolt, type on a keyboard, operate a joystick, and insert a USB stick. Cameras on the forearm and gripper provide optical feedback and depth perception inside the base station, while a camera on the back of the rover provides an alternate viewing angle of the arm's relative position.
For the autonomy mission, Helios utilizes a differential GPS for precise point-to-point navigation. During navigation, the rover utilizes our new Triclops camera layout to stitch together images from a Z2i stereo camera and 2 180-degree side cameras to create a larger field of view. 2 asynchronous computer vision algorithms allow the rover to autonomously navigate to its goal. The first algorithm detects AR tags using OpenCV's Aruka library. The second allows us to avoid obstacles seen in the Zed's 3D point cloud using a custom trained YOLO model and an A-star pathfinder. Upon successfully reaching a GPS waypoint, our rover will enter into a search pattern state and spiral outward until the AR tags are found. The rover will then enter a new navigation routine to either approach a single marker or maneuver through a gate. Completion of the task will then be indicated using the LED panel on the back of the rover. Utilizing old rovers and the Weebots robot simulator, each new feature goes through a rigorous amount of bench and field tests before a final review and ultimate push to dev.
Our redesigned science gantry system now utilizes carbon composite tubes to reduce the weight by 33% while improving rigidity. To analyze soil samples, we lower our updated instrument array into each sample site. Housed in an electroplated casing, our new custom fluorometer uses 6 UV LEDs and an optic system to induce fluorescence for the detection of life. Receiving between 330 and 600 nanometers, amino acids and carbohydrates can be detected. It is paired with a microscope capable of 400 times magnification, allowing us to see sediment grains within the soil sample. Finally, gas sensors allow us to measure the carbon and nitrogen biological cycles in action. Helios is also able to run a series of chemical tests along with its instruments. Using a multiplexing water distribution system driven by a peristaltic pump, our latest chemical suite utilizes the ninhydrin and Benedict's test to look for amino acids and reducing sugars in our soil samples. After analysis is complete, a soil cache box allows us to collect up to 10 grams of material with the highest scientific value for future analysis.
The creation of an R&D division has enabled our team to explore more ambitious ideas and processes while maintaining our ability to address issues identified during previous URC missions. We have placed a heavy emphasis on structural composite components, spectroscopy methods, electroplating techniques, and brushless manipulators to incorporate into future designs.
Thank you for your consideration. The Mars Rover Design Team looks forward to competing at the University Rover Challenge this June. We're going to have a panel with some of our team leads who are going to be able to ask. You guys are going to feel free to ask any questions you might have about any of the technical parts of the rover. If you have any questions about how we do some of our circuit boards, how we do some of our manufacturing, how we do, you know, this or that. It's going to all be up to you guys. So if anyone has any questions, I will make a line somewhere and can ask the questions. Let's make a line going down this way. I don't know. Do you guys want chairs? Do you have a question? Okay. Do you have a question? Yeah. Could we please have one of the team leads talk about the autonomy system on the rover? You have to project, Brady. The microphone's not working. Yeah. Well, it's working for the setup. He doesn't. It's not making me louder. Huh? It's not projecting to the speaker.
What was the question? So the autonomy system uses our stereoscopic camera. It feeds that information into a state machine. So based on what it sees, it goes into different states, and we can adapt it to like obstacles or whatever gate or waypoint we see. They give us GPS points, so we have to go to each of those in any order. So we just program those in and tell it which order to follow. Right. Yeah. The actual autonomy system is like on the rover, so we just send the GPS points to the rover, and the GPS and computer on there figure out where to go. Yeah. We use a YOLO model, so you only look once. It's a neural network that figures out what it's looking at and whether it needs to avoid it or not, and then if it does, we use an A-star algorithm to navigate around it. It basically figures out a big grid and then places the obstacle on it where it sees it, and then yeah. I don't work on autonomy much at all. That's all those guys over there. I work mostly on base station and the networking. No problem.
So, can you tell me some of the research projects you've been doing? You can tell me some of the research projects you've been working on?
Recording? Yes, some of the main research projects we got going on are a lot of carbon fiber development, so switching our traditionally aluminum parts to carbon fiber in order to save weight on our rover. One part that's on the rover is the carbon fiber diff bar, on our current rover. It's been performing really well. We're working on making a carbon fiber bicep for the arm, carbon fiber C-links. There's Jacob posing with it over there. But yeah, as well as rotating signal stack is another one we have a group of people working on. So having 2 signal stacks and one of them rotating so we can basically control where we're pointing our signal stack to during competition. One that we got started is a brushless arm, so an arm using brushless motors. That way the electricals can start working on controlling those. So yeah, a lot of exciting stuff going on.
So it looks like we're gonna cut back to Max here, and he's got some announcements about. You guys really like what you've been doing, what we've been doing here today, and like you want to support us, you want us to do more research projects or continue to build a rover, build more rovers, go to more competitions. Then listen to what Max has coming up. He'll talk a little bit about how you can support our team.
All right, Eli, we're good on audio right now. All right, everybody. One last thing, we're going to kind of pivot this a little bit impromptu. So because of the issues we've been having with the microphones, we're going to have our team leads around. Anyone in a polo, anyone in a Mars Rover Design Team shirt, feel free to go ask them about anything on the rover. They should know something about it. If they don't, they can direct you to someone who does. While I have your attention here, building a rover is many things. It is challenging. It incites passion. Want to know what else it is? Expensive. So we have started our crowdfunding efforts. If you text Helios to 41444, you can donate to the design team to help us fund not just the rover, but any of the incredible research projects and any of the incredible PR, anything that the team needs to operate. Having the ability to help us out in any way possible, we very much appreciate and would be grateful for. So again, that's text Helios to 41444, and you can help us. What we're going to do now is all the rover members, the students themselves, if you could all join us over here, we're going to take a group photo, and then we're going to open up Helios and the backdrop for photos of any. From this moment on, Helios is unveiled to the world. Feel free to post as much as you would like about Helios, about any that we've seen today, about any of the people. I would love to see my Instagram feed flooded with all sorts of things. So if all the rover members could please join me up the stage over here, we're going to start framing a shot. And then at the end, we're going to allow you guys to keep mingling so that we can continue our live stream and keep learning about this incredible system and team.
kind of an overview of what the system is. This is the science analysis system on the Mars rover. So the way the competition works is we're supplied with 6 soil sites, and we have to determine if there's extinct or extant life in it. And the way we accomplish that is by moving the gantry over, dropping down our 3D printed scoop down to a soil site, and then you can see the scoop open, pick up some soil, bring it back up, and then deposit it into our 3D printed funnels. Once it's deposited, we can use a custom water multiplexing setup to deposit water in the soil, and you can see as it moves across different channels here. Once water is deposited into the soil, it will run through the funnels and then down into these test tubes. And these test tubes have been preloaded with chemicals from our science analysis team. If you see the silver blocks, those are our heater blocks, and the purpose of those is to heat the chemicals up to 100 degrees Celsius and catalyze the reaction to a visible result that we can view on camera. Okay. And then finally, on our sensor side, we have a microscope and custom fluorometer. That'll look for signs of life just by using fluorescence, and then also visibly looking for cells.